Hello, welcome to the first lesson in the core unit, hazards. Actually, it's official things, tectonic processes and hazards for the Edexcel A-level geography course. Physical unit, which goes with paper 1. The format of this is in section A, where you do a 4 and a 12-mark response. So this is an introduction to it and kind of very much kicking off with the Earth structure and the theory of plate tectonics. So let's be a little bit more specific. So there are different sections of the specification. On this particular slide, I've got 3 sections out of the what we call the inquiry questions. So this one here is positioning about why is it some areas are more at risk from tectonic hazards. So tectonic hazards, the 3 main ones are earthquakes, volcanoes, and tsunamis. So in this first lesson, I won't necessarily do it in the exact order that you see here. But ultimately, I'll cover these 2 areas here. But I'll slightly do a bit of a recombination of it, just the order in which I teach it at. But it will cover all of these things here. Okay, so let's move on. So to understand plate tectonics, first of all, we need to have an idea of the Earth's structure. So the picture that you got here kind of still holds true, but this is what you would have probably been shown in year 7, 8, or 9, maybe primary school, possibly at year 10 and 11, but it's a little bit more complicated than that. If we look here, we have the layer, the crust, which is the thinnest layer that we talk about, the layer that we live on or life is on. We have this molten layer under here called the mantle, which is made up of magma, an outer core, which is more liquid in nature that spins, and then a solid inner core. And the basic premise here is it gets hotter as we descend. The reality is it is more complicated than that, but the fundamentals are still true. So on this slide here, again, I'm still retaining the 4-layer structure, and you can see there are some specifics of information here. Just to give you a little bit of an idea, the crust itself, there are 2 types, ocean and continental crust, and where the continental crust is, it can be up to about 70 kilometers thick, where the ocean crust is probably as thin as 4 kilometers thick, probably middling average around about 30-ish sort of kilometers in thickness. The biggest layer is this layer here, what's full of magma, molten rock. That's just under 3,000 kilometers thick. Okay, so the biggest layer. The outer and the inner core combined are probably about the size of Mars. Now, on this diagram here, this is more one of you utilizing it and seeing just if you can like pause the video, can I remember the 4 layers? And we're not really even into A-level territory here, but remember we're trying to put some of the fundamentals in to understand the bigger stuff that allows you to understand things like plate margins, why volcanoes erupt, why earthquakes occur, tsunamis, etc. Here there are more specifics, and again I've alluded to about the thickness of the crust, very thin layer, the mantle. This does have subdivisions which I'll reveal more on the next slide. And the outer core is very important. It creates a magnetic field because it spins. It probably contributes a little bit to gravity, and also protects us from some of the harmful radiation that's emitted from the sun. And this really here is the engine of the Earth in terms of the heat that's generated from it. Mixture of sort of radioactive decay and primeval. I've never remembered if it's primordial or primeval heat, kind of like just decay. So a layer that you really do need to get to grips with. Some students struggle with this, and this is a little bit of a confusing diagram, only in the sense that it's busy and it's got lots of colours. But if we just look at what we've taught, there is still the crust, that mustardy yellow colour, I would say. And then if you look carefully here, this grey area down to this light peachy colour, that's still the mantle, but you can see it's been broken up into some sub layers. That's the difference. Then you go down to this outer core, more sort of liquid than molten, and then what we think is a very solid layer underneath that called the inner core. It's this first bit up here that we need to make sure that we address. If I move the mouse over here, there's this label here called a lithosphere, and it's important that you pick up on that because the lithosphere is the crust and the very top part of the mantle, this thin slither. By the way, remember, this is not to scale. And if you look over here, that crust with the lithosphere can be just over 100 kilometers in thickness. This grey area is almost like the connective tissue to the mantle. So it's part of the mantle, but it's also part of another layer called the lithosphere. So the lithosphere is the crust, and as you can see here, the uppermost mantle. This can change in depth, density. It's more malleable. It is slightly plastic in nature as it will deform, but it doesn't flow. The next layer under here, which is probably another 200 kilometers, this is where they think the rock is particularly molten. But even if you combine this and this, it's a small fraction of the rest of the mantle. And when I go beneath the asthenosphere, you can see there are more sublayers. There's a layer called the mesosphere, and there's probably more sublayers as well. But we don't need to concern ourselves with that. We need to be aware of what the mantle is. But particularly, I think the crust, the combination layer, the lithosphere and the asthenosphere, you do need to have some knowledge of that. Mainly because a lot of the diagrams that are thrown at you are referencing these sources. And remember, you are doing A level, so you do want to pick up on the expertise of this. And again, just look at how thick the lithosphere, or the crust part of the lithosphere, is when we're on land. That's a mountain, hopefully quite clearly. That's 70 kilometers probably, and that one there is really, really thin in nature. So summing up just a couple of key facts that you should be aware of. The lithosphere, remember, that's the crust and the upper part of the mantle. And you'll see different things here. Remember, that's a combination. That's not just the crust on its own. So between 70 and 250 kilometers thick. Said that, I think this is less important. That stands for silica and magnesium, and that stands for silica and aluminium, kind of like indicating the prime makeup of it. There's an average. And then we've got some specifics here that I would learn, right? I mean, the key thing to remember about the ocean lithosphere or ocean crust or continental crust, etc., is that the ocean crust is thinner but denser, and the continental crust is thicker, less dense. It's important to get that because that has an impact on the plate boundaries that are formed. So focusing a little bit more on crust, let's view this in just a little bit more detail. So again, and we can see there's a bit of overlapping taking place here, right? So consolidation, I'd call it. So there's the crust part, there's the continental crust. There's the rest of the lithosphere, which is the upper part of the mantle. And then you've got the ocean crust here, much thinner. This is denser, therefore behaves like it will always go underneath the continental crust. And then you've got the rest of it here. There's a little bit about the scale. And if you want to look at this a little bit more simplistically, here we go. Well worth looking at this just to, again, could you draw this table out from memory? So again, you could do a pause. I don't really think you need to know about the density figures of 2.6 and 3. But I think knowing the thickness, at the very minimum, one is thinner than the other, one is heavier than the other. This is one of interest. Continental crust, generally, as an overview, is much older. A lot of it's much more stable. Some of the oldest rock that exists. If you really get into it, you can learn about cratons and things like that. And ocean crust is quite young, 200 million years. Saying that's young, from our perspective, that's an inordinately, unimaginably length of time. But that's 1.5 billion. That's measured in the hundreds of millions of years, created and destroyed. Again, these sorts of things, yeah, knowing about basalts might help a little bit, but this is more your extension knowledge. It's rare that you would talk about this in any sort of depth. The 4 marks are skills questions anyway, and the 12 markers, you're a bit limited to how much you can write. But again, you should never just teach the spec. You want to become the expert in the field. It makes it more interesting as well. Again, just a few things to sum up on the mantle. Overall, so some key figures, depths, temperatures, etc. That should say degrees. And then this very important word, convection current, takes place here. Again, just a few things about the asthenosphere. The word for that is weak kind of rock. And again, there's this focus on the melting zone where the rocks are capable of flowing because they're molten. Remember, they're not liquid. And there's that layer there. Remember, this is not the scale. And again, you need to have an awareness of this. Temperature, that's liquid spins effectively, but you're not going to get questions that really concentrate too much on that. Right, so magma, generic word for the rock that's in the mantle. It's molten. Now, technically speaking, this isn't magma because it's on the surface. It just happened to be the pictures that I selected, and I thought they were quite visual. Um, so this, technically speaking, is lava. And when lava comes onto the surface, it can behave in all sorts of different ways, such as, it can be really slow and bubbly, and some of it can act like fireworks. And so it has different consistency. So it's got the solid part, which is kind of the mineral content, a liquid part, and it also contains different sorts of gases. And that can determine land forms, but also things like the type of volcanic eruptions that take place. Um, I mean, I'm talking about the core and the outer core and things like that. And there's a lot of figures here. I mean, again, you probably always learn a bit more than you need to. Just more of an awareness of what they do, the function they do. And I would say majority of the units focusing on the really kind of on the lithosphere and fed by the mantle. Okay, checkpoint. So one of the checkpoints you can do, two things you could do here. Pause the video and then just do what we call a blurt, where you just write down everything like keywords that I've just talked about for the last 10 minutes, right? Everything that you've learned about the Earth structure, right? So you can do that, or you can have a go at doing this quiz. Now this layer here, well, it depends what level you're doing it as. So although I've got answers, I've based the answers based on Key Stage 3, those things you'd have learned. Okay, so again, if you want to have a go at doing this quiz, it's only one word type sort of answers. Pause the video, have a go at doing it. Welcome back. Here are the answers, so just review them. So like if you're breaking the mantle down into its sublayers, then obviously it's going to be more than that. So obviously you play to that. I didn't mention this specifically, although I talked about them. There are two main types of crust, ocean and continental. We talked about that. Let's have a look as we further down. The convection current, that's a circular movement of the magma. You'll see this also in atmosphere and the ocean currents. It's how kind of liquids kind of move when they're heated up and cooled down. So that's talked about quite a lot in geography. So it is important to get that concept. And it's a key player in understanding why plates move. That's the Earth's crust. Let's move down here. I don't think there's anything extra that I haven't already talked about. This bit I haven't mentioned, so this is kind of like a move forward ahead. But you may remember from GCSEs, plate is a giant slab of the Earth's crust or lithosphere. There are many of these on the Earth, and where they meet up, we call it a plate margin or a plate boundary. And continental drift is the theory of how the Earth's plates have moved around. Let's have a look at these plates next. So very, very colourful map. You can hopefully you can work out, you can see these different continents that you've been taught about in geography, and then you can see these darker lines here, and then you see these coloured areas here. So all of this, by the way, is the North American plate. We've got the Pacific plate, the Eurasian plate, which extends across here. So we're saying that the Earth's surface is fractured into giant plates, and they sit on top of the mantle. Now, this doesn't allude to what's taking place. The next slide will do that, albeit a bit busy. Again, just give your eyes time to acclimatize to this. So the purple lines represent the boundaries, the plate margins, and in between you can see words in capitals like North American, Eurasian, etc. They're the names of the key giant plates. There are lots of smaller ones, and then the arrows allude to what's taking place. So some plates, if you look here, you can see this is moving in that direction, that's moving in that direction, so they're moving apart. And then in this one here, you notice these two arrows are moving sort of similar directions. And then in this one, if you look here, you have to look quite closely. The arrows are converging. So the words divergence and convergence are used in this unit. That just is a description of the movement. So these are diverging apart, means moving apart. Where they're coming together, they're converging, and where they slide past each other or slide in the same direction, they call it conservative. This is a slightly more complex map in the sense of the numbers represent the millimeters a year they move. Okay, and then the coding here on the key represents the type of plate boundary. I haven't mentioned collision, that's another convergence zone. And then here you've got like some specific names of places and so forth. It's good to see these sort of maps because they're the sorts of maps that you get in exams and you have to be able to interpret. So some of the plate movements, so absolute velocity means the fastest, that's centimeters per year. And if we just hone in here, the Coscos plate here, that's 8.55. So unless I've misread that, I think that's the fastest one on here. And you can see some plates are moving more slowly. So this leads to, and I've said it on the previous slide, this. I bet some of you know what this is already. But just leave your eyes, take your eyes on this. Well, clearly it's a computer animation. But this is what they think has happened in the last, I don't know, 200–300 million years. And if you focus on, hopefully you know, whereas South America and Africa, let's just clicked off that, they look like they were together. We call that the jigsaw fit. You can see them just moving apart. And there's lots of evidence to support this. I'll do the evidence on another video. So I'm trying to give more of an overview that links into the first part of the syllabus. And now if I go to the next slide, we can break this down a little bit more carefully. So it's the theory, it's called continental drift theory. So a gentleman back in the early 20th century made lots of observations on like geology, biogeography, that's like plants, vegetation, etc. And came up with this idea that the continents that we know and love today were in a different position. And he didn't necessarily give the exact timescale for this, but we had a supercontinent called Pangaea. And over time, if you've got the time here, it's gone, there's been this separation to the present day, and that's kind of alludes to this very, very fast animation on the slide there. And then there are scientists saying that in the next few 100 million years, they'll all converge together. I think it's Ultima Pangaea or Pangaea Ultima. And so there's this kind of movement. And that has really gained traction in the last 50 years. So the early people in this, and it goes back before Alfred Wegener, it really has become the accepted theory since, I think, early 1970s. And there's work by people called Hess, Ewing, and a few others, where they, things like, with all the data coming in from earthquakes and geology and sonar readings from off the ocean floors, they kind of like come up with a theory that really, really works and has been accepted by the scientific community. So let's have a look at that process. So one of the key things here is, remember we said that the lithosphere is broken up into giant slabs. They're called plates, and where they meet up, they are plate boundaries. This first theory still holds true. It's still reckoned to be a driver of it. It's called the convection cell theory, or convection current. And if we look here, we can see this circular diagram here. This represents the movement of magma. And as it passes the outer core, we're saying it heats, it expands, it rises, upwells, and then moves across, pushes and pulls the plate along, and then cools, gets denser and descends, and it's repeat, repeat, repeat. Okay, so that theory definitely you need to know about because it explains plate movement. If you explain plate movement, therefore you can then explain things like the landforms, ocean trenches, for example, ocean ridges, island arcs, volcanoes, and events like earthquakes. Let's have a look at the video in action. So I think this does this nicely. What you need to do is get a narrative to this, almost like a storyboard for this, which we'll show a little bit later. This just is maybe a more simplistic way of the same thing. Now, this static picture, again, it would be good for you to pause and maybe do because it's two-dimensional, like without the color and everything here. So I've broken it down into 5 steps. So step 1 would be the magma as it flows past the outer core. Remember, this is very, very hot, 3,000–4,000 degrees. As this magma goes past this, it obviously it heats up, it expands, it upwells, rises, because it's lighter, more buoyant. And as we get to the top here, some of the magma goes up and forms new plate. Now, this should really be like a ridge. It's flat edged there on this particular diagram. Forms new crust here at the top part. Too hot down here. Now, that crust has to go somewhere, so it pushes the crust. I'll talk more about that later on. Now, the majority of the magma is deflected. That means bent to the other side. And as it travels under the crust, it kind of pushes and pulls it along. And as we go then to the, I don't know, north, south, west, it depends on the perspective here. It's getting relatively cooler and it gets denser, so does the crust itself. There's a bit of a deflection of the crust here as it's bent downwards, and then the magma flow here is deflected downwards and it returns back down to the outer core if we take this at face value, and then the whole process is repeated. And therefore, like a travelator at an airport, this plate gets moved apart. Now I've put that into 5 steps. So I'm not going to repeat all that. So if you read this slide, that will give you the essence of that. So this takes you through those 5 points. I can't go backwards on this because it doesn't allow me to do that. The video is linear in that sense of the word. So if you learn these, that's the essence of what I talked about. I think a very important process to learn. I've already talked about seafloor spreading, but I will repeat it. But there are additional theories, ridge push, gravitational slide, and slab pull, which are additional bits of theory which don't contradict the convection cell. The convection cell we think occurs, but a lot of people think, or scientists think, that on its own it's not enough to explain the full story of what's going on. Now, this particular picture is quite good for showing what we need to see. So again, if we look at the perspective, here's our mantle, magma rising. This doesn't show the convection cell, but if we look here, this bit we have talked about, and I mentioned prior to a few minutes ago, the magma rises up here. Now it's too hot where the mouse is, but once it gets high enough here, the temperature's cool, rock is formed, as in crust is formed. It has to go somewhere, so it shunts the older crust to the sides. And actually, if you date the rock as you go this way, it gets older, right? So it's pushed to the sides. The other thing here is, because it cools at this point here, it creates a ridge. This is not some small ridge. This is, in some instances, 2 to 3 kilometers high under the sea. That creates a high point. And just like if you sit at the top of the slide and then you push off, you go down, you gain momentum because of gravity. So we've got extra crust being formed here. That pushes the cross, that's the ridge push, and the gravitational slide is the assist by gravity aiding the movement here. So this, if we circle here, we've got extra crust, we've got the gravitational slide pushing and aiding the convection current. Notice as we go, I'm going to use left. If we go left on this diagram, don't like using that word really. Notice that the lithosphere is thickening. That means it's getting denser, collides with this continental crust, and is deflected downwards. And that's slab pull. You'll see, I'll demonstrate this on not the next slide, but the one afterwards. And it's like where you get a chain with a plug on it. You demonstrate in front of the class. You push the plug towards the edge of the desk. One extra nudge, the plug descends to the ground and pulls the chain afterwards. And it's pulling it, gravity assist. So we've got pushing and over here, convection cell here, and we have the pulling here. Definite theory that you need to be aware of. So like at GCSE, often we just teach convection cell, but you need that seafloor spreading, you need that ridge push, and you need that slab pull. Okay, so this is the ridge push. So this point here, extra crust here, has to go somewhere, so it shunts it that way. And you can see a bit of the ridge. So we've got the gravitational slide. The convection cell's not shown on here. And I need the next slide to show you the slab pull in action. There we go. And I'll talk more about, well, let it come back to the original slide. This goes underneath this because this is denser and this is less dense, and as many of you know why, but I will repeat that, but that's in a few lessons' time. Now, on the next slides, I literally just rush through these because on these there's much more depth, reading depth, I would call it. So I don't want to kind of just repeat for the sake of it and make the video overly long. But read through these slides. You can get the PowerPoints for this if you're on my course, and or you can make notes off the video. And this is just stuff in a bit more depth. You can see about the seafloor spreading. And then we've got a couple of slides just kind of extending the ridge push and slab pull mechanisms, and a few kind of advanced points, nothing to really worry about, just more detailed information. And then just to finish off with, because this is in that first part of the spec here. So one of the things that we need to look at here, there's two maps we'll look at, and a clear link between plate boundaries and earthquakes. You get earthquakes at all plate boundaries. It doesn't necessarily show up on this map brilliantly. You can see there's a blue line, that's a plate boundary. It doesn't have it there, but we do get earthquakes at all plate boundaries. Some are worse than others. But the other thing that you need to be aware of is what we call I-N-T-R-A, intraplate earthquakes. Look how far these are away from the plate boundary. So that's something that will be explained in this course. Okay, you can see some more scattered across here. Certain types of plate boundaries, conservative and convergent boundaries, tend to have the strongest earthquakes. And then if we now go on to the next bit, okay, here we have, these aren't all the volcanoes. Obviously, the earthquake events, there are thousands of earthquakes happening every day. This represents some of the active volcanoes. There's something like 500 active volcanoes on land, by the way. There are more under the sea. And you can see, again, there is a strong connection of volcanoes and plate boundaries. But you also get them in places, again, thousands of kilometers away from plate boundaries, and these are known as hotspots or magma plumes that come up from the outer core, okay, through the mantle. And again, look, you can see loads of these scattered well away from plate boundaries. This doesn't show all the plate boundaries, by the way, but at least you get that idea. And these are just like really famous volcanoes that have taken place. This course will cover that. So at the end, we've come to the end of the slideshow. So in this one here, I've talked about really plate tectonics, in a nutshell, the theory of plate tectonics. Talked about the earth structure, which is key to giving the substructure to all this. Talked about what plates are, plate boundaries, not gone into any depth on that. And then talked about the fundamental mechanisms by which they move. That's convection cell theory, ridge push theory, or gravitational sliding, slab pull, forgot to mention seafloor spreading, and also the pattern where we get earthquakes and volcanoes. And I also brought in some terms that maybe you haven't done at GCSE, and that would be hotspots theory with the volcanoes and intraplate earthquakes. Thank you very much for listening to lesson 1. I will see you lesson 2.